Welcome to Chapter 17 on Hearing and Music. This is Section 4 on the Doppler effect. The Doppler effect is a shift in frequency due to relative motion between the source of the frequency and the observer. The Doppler effect is the cause of the kind of characteristic sound you hear for racing cars. And forgive, I will do my best here. It's kind of like, meow. I know. Horrible, but I tried. When this happens, there are two effects. One is a change in intensity, a change in volume as the object moves closer to you or further away from you. That is not what Doppler effect is about. Doppler is all about the change in frequency. To illustrate that, the first thing we're going to go do is look at this website. So on this website, what we have is an airplane. Up here in the corner, it tells you the ratio of how fast is the airplane moving relative to the speed of sound in the simulation. Right now it's at 0 because the airplane is not moving. And you can see the airplane is producing sound as illustrated by these purple rings. And right now, every portion of those purple rings is equal distant from the one next to it, showing that no matter where I stand relative to this airplane, the frequency I'm going to hear is going to be the same. You can think of those purple rings as representing the crests of the sound waves coming out of the airplane, if that helps. Okay, so now let's do this again, but let's let the plane move a little bit. And I'm going to take it to extreme, where the plane is moving at half the speed of sound. So now you can see that these sound waves in front of the plane are closer together than the sound waves behind the plane. Because the sound waves are closer together in front of the plane, that is going to make for a different wavelength than behind. And in front, the observer is going to hear a higher frequency known as a blue shift. The reason it's called a blue shift is because in light, blue wavelengths have a higher frequency than red wavelengths. Behind the plane, the wavefronts here are further apart. Therefore, that's going to result in a lower frequency observed, or a red-shifted frequency. If I again run this, but I bring the plane up to where it's almost at the speed of sound, so we're going to go with 0.9. You can see that the wavefronts in front of the plane are still in front, but they're all very much on top of each other. So we've gone to an extreme with this. And again, if I take it so that we have exceeded the speed of sound, so now this plane would be flying at, say, Mach 1.2. Now the wavefronts are no longer in front of the plane. And so when the plane hits an observer, say down here, all of the sound wavefronts hit at the same time. Oh, they didn't quite make it. We'll move our observer back a little bit. Therefore, the person here would hear a sonic boom. Right? So going back to our PowerPoint slide, summarizing really quick, if the source and the observer are moving closer together, then the observer hears a higher frequency known as a blue shifted frequency. And if they're moving further apart, if you're standing behind the plane, then you hear a lower frequency, a red shifted frequency. A sonic boom occurs when the source travels faster than the speed of sound wherever it is. The first link on this slide is the same simulation we just looked at. The second link is a YouTube video showing a plane exceeding the speed of sound. So if we pull that up and watch, I'm going to pause the video when we get to the spot I want to talk about, which is right here. You can see the cone that's forming around this plane. That cone is due to all those sound waves affecting the pressure of the air behind the plane, which lowers the temperature of the air behind the plane. And because the temperature lowers, the water is able to form go from being a gas to being a liquid, it condenses, and therefore you get a cloud forming in that region. Other videos of this nature, if you just Google or type into YouTube, plane exceeding the speed of sound, have sound associated with them so you can hear it. This one does not. So going back to our PowerPoint slide here, there are ways to write the formulas for the Doppler effect where you have one formula that does it all. I choose to keep the motion separate. So we're either going to look at the fact that the source is moving or the observer is moving, but we're not going to have a situation where both the source and the observer are moving simultaneously. It just simplifies the math a bit for you. Okay. So first off, let's consider a moving source. Okay, so if we have a moving source, then the observed frequency is calculated by taking the frequency of the source and dividing by 1 minus over plus the speed of the source divided by the speed of sound. And now you're looking at it and going, minus plus here, Dr. Murphy. Yeah, sorry about that. The minus sign corresponds to when the source is moving toward the observer, and the plus sign is for when it's moving away. So that's not as bad as you might have thought, right? And now for the moving observer. If you have a moving observer, you get a slightly different formula. In this case, the frequency of the observer is the frequency of the source multiplied by 1 plus or minus the speed of the observer divided by the speed of sound. And now plus or minus. Same thing as above, but regrettably they switch. So in this case, the positive sign, the plus sign, corresponds to moving toward, and the negative sign, the minus sign, corresponds to moving away. If you notice, when they were written, in the top equation here, the subtraction is on top and the addition on the bottom, and in the lower one, the addition's on top and the subtraction is on the bottom. The reason for that is so that the top symbol, in this case subtraction, means moving toward. The top symbol here, the positive, the plus, means moving toward. That way, it's easier to remember which one is doing what. The positive, or not positive sign, the upper of the two signs corresponds to motion toward, and the lower of the two operations corresponds to motion away. Now, I made an Excel spreadsheet for you. I will put it in the resources folder on Sakai so you can go and play with it and look at it, where I graph the results of these two equations for you. So first we're going to look for a moving source. For this Excel spreadsheet, the frequency of the source was assumed to be 500 hertz, and the speed of sound was 343 meters per second. Blue corresponds to moving toward, and orange corresponds to moving away. You can see here that the observed frequency shifts more as the source is moving faster, particularly when it is moving toward at nearly the speed of sound. The orange line, or the orange graph, looks like it is linear. It is not. You will see that in a couple of slides. It's just not as dramatic a change as it is for when we're moving toward. Now let's look at the observer moving. Again, blue is moving toward and orange is moving away. Same parameters, 500 hertz for the frequency of the source and 343 meters per second for the speed of sound. These equations, or these graphs, are linear, and you get nearly the identical shift moving toward and moving away for the observer. if I plot the two graphs for moving toward each other, so blue is the source moving toward the observer, and orange is the observer moving towards the source, both give us an increase in frequency as the speed approaches the speed of sound, but the source moving gives us a more dramatic shift in frequency. And lastly, if I look at the moving away, again, blue is the source moving away, and you can see the nonlinearity in that graph now. Orange is the observer moving away. Again, both of them have a shift towards lower frequencies, redshift. The orange, the observer moving away from the source in this case, gives us the larger shift. Again, these graphs were made with an Excel spreadsheet, and I will put that Excel spreadsheet up on Sakai for you so you can see what happens if you change the speed of sound or change the frequency of the source. Next, I want to go through 3 sample calculations with you for this. Here is the first. We have a siren at 300 hertz moving at 25 meters per second towards you. I want to know what frequency that you would hear, assuming that the air temperature is 20 degrees Celsius. So this 300 hertz, that is the frequency of the source. I am told that the source is moving towards me, so this 25 meters per second is the speed of the source. Oh, that's SRC, not SCR. And it's moving toward me, so that's an important piece of information we need. The 20 degrees Celsius is a temperature, but remember, if we know the temperature, we can get the speed of sound. That number will lead to that. Let's start with that calculation. So in this case, the speed of sound is going to be 331 meters per second times the square root of the temperature in Kelvin divided by 273 Kelvin. First thing you need to remember is that to get from Celsius to Kelvin, I add 273. So my temperature in Kelvin will be 293. So 331 meters per second times the square root of 293 Kelvin divided by 273 Kelvin. And that results in 331 times the square root of 293 divided by 273, 342.9 meters per second. I'm going to round that up to our standard 343 meters per second. Now that I know that, I can figure out the observed frequency using my Doppler formulas. I know that I have a source moving towards me. Therefore, I want to use this formula. The observed frequency is the source frequency divided by 1 minus, it's minus because it's moving toward, speed of the source divided by the speed of sound. So the source frequency is 300 hertz. 1 minus the speed of the source, I'm told, is 25 meters per second, and we want to divide by 343 meters per second. And if I put that all into my calculator, 300 divided by 1 minus 25 divided by 343, I get 323.6 with a little bit of rounding hertz. That's the end of example 1. Example 2, we're going to be moving away. I hear a siren at 100 hertz. Oh, sorry, that's 1,000 hertz. This is telling me what is being heard. Therefore, this is an observed frequency. I am told I'm the thing that's moving. So the observer in this case is moving away. Let's underline that. And it tells me how fast the observer is moving. In this case, it's 20 meters per second. Here we're told the speed of sound is 343 meters per second, and we want to know the frequency of the siren. So in this case, I need to use the formula for a moving observer, or an observer moving away. So that would be the observed frequency is the source frequency multiplied by 1 minus the speed of the observer divided by the speed of sound. I know that the observed frequency, the frequency that is heard, is 1,000 hertz. The frequency of the source is what I want to find. What frequency is the siren producing? And I multiply by that 1 minus 20 meters per second over 343 meters per second. So if I take and put 1 minus 20 divided by 343 into my calculator, that gives me that this is the frequency of the source multiplied by 0.94. That still has to equal 1,000 hertz. So in this case, the frequency of the source will be 1,000 hertz divided by 0.94. If I take 1,000 and divide by that answer, that results in a frequency of 1,061.9 hertz. And that would be the frequency that the source is producing. Because it's moving away from me, the frequency that I hear is redshifted to a slightly lower frequency. For our next example, we want to determine how fast is something moving, we don't know yet, and in what direction. So I hear a siren at 400 hertz, so this again, because I'm hearing it, is the observed frequency. I know that it is from a source that would produce a 300 hertz siren, so this is the source frequency. I want to know how fast is it moving and in what direction, and again I'm told the speed of sound is 343 meters per second. So the first thing I'm going to do is I'm going to look and see, 400 hertz, 300 hertz. The observed frequency is higher than the source frequency, therefore it is a blue shift, and I know it is moving toward. Okay, it asks how fast is it moving? Well, the it in this case refers to the siren, so we have a moving source, and it is moving toward. So again, that would be this formula. So the frequency that is observed is the frequency of the source divided by 1 minus the speed of the source divided by the speed of sound. So there is a bit of math that has to be done here, a bit more than what we've done in the past. So the observed frequency is 400 hertz. The source frequency is 300 hertz. And I am subtracting 1 minus the speed of the source, which is what I want to find, over the speed of sound, which I'm told is 343 meters per second. Okay, so the first thing I'm going to do is I'm going to move the denominator up and multiply it by the numerator. So 400 hertz times 1 minus the source over 343 meters per second has to equal 300 hertz, or in other words, 1 minus the speed of the source over 343 meters per second has to equal 300 hertz divided by 400 hertz, which is 3/4. I'm now going to subtract 1 from both sides, so I still have a negative sign up front here, so negative the source over 343 meters per second has to equal negative 1/4. I now have a negative on both sides, so I can cancel it. And to find the speed of the source, I need to take 343 and divide by 1, or multiply by 1/4 or divide by 4. So 343 divided by 4, that tells me the speed of the source is 85.75 meters per second. And again, that 85.75 is 343 meters per second divided by 4.